Go.
By the first millisecond, the universe had cooled to a few trillion kelvins, and quarks finally had the opportunity to bind together into free protons and neutrons. Free neutrons are unstable with a half-life of about 10 minutes and formed in much smaller numbers. The abundance ratio was about 7 protons for every neutron. Before one neutron half-life passed, nearly every neutron had paired up with a proton, and nearly every one of these pairs had paired up to form helium. By this time, the universe had cooled to a few billion kelvins, and the rate of nucleosynthesis had slowed down significantly. By the time the universe was 3 minutes old, the process had basically stopped, and the relative abundances of the elements was fixed at ratios that didn't change for a very long time. 75% hydrogen, 25% helium, with trace amounts of deuterium, hydrogen 2, helium 3, and lithium 7. Big Bang nucleosynthesis produced no elements heavier than lithium. To do that, you need stars, which means waiting around for at least 200 billion years. More than 90% of the universe is composed of hydrogen and helium. Both elements have been around since shortly after the beginning of the universe. Yet, hydrogen and helium together won't make anything as complex and as interesting as the Earth, or a bacterium, or a refrigerator, or you and I. To do that, we need carbon and oxygen, and nitrogen and silicon, and chlorine, and every other naturally occurring element. Almost all of the hydrogen and helium present in the universe today were created in the first 3 minutes after the Big Bang. All of the other naturally occurring elements were created in stars. You need really massive stars for this, say 20 to 120 times the mass of the Sun. Really, really heavy stars do something different. The mass 5 and mass 8 bottlenecks. There are no stable isotopes having atomic masses 5 or 8, but there is always a very small amount of beryllium at any moment that is available to fuse with a third helium to produce 12 carbon. This extremely improbable sequence is called the triple alpha process because the net effect is to combine 3 alpha particles to form a 12 carbon nucleus. The triple alpha process is not relevant in main sequence stars like the Sun because their core temperatures are too low. However, in the red giant phase, after many stars have accumulated vast amounts of helium in their core, the central temperature can rise high enough to initiate the triple alpha process.